Hi everyone, we are presenting today our project on chest X-ray pneumonia detection with attention mechanisms. My name is Adam Abarbash, and together with Adham Hassan, we have developed an enhanced deep learning approach to improve medical image classification, specifically for the problem of pneumonia detection. The problem statement is that pneumonia remains a critical global health issue and actually causes over 800,000 child deaths in 2017 alone. And the issue with traditional diagnosis is that it relies heavily on radiologists, but this process remains to be subjective and quite prone to human error. And some rates observing the failing of such observations as low as 70% to 85%. So to tackle this issue, basically, we want to automate this process in order for us to have a faster and more consistent diagnosis of such medical cases. So the baseline model that we selected for such a job is the DenseNet 121 integrated with the CBAM module, which is the convolutional block attention modules. And we chose this specifically because DenseNet is quite parameter efficient, as we can see in this comparison with the other models from the literature. These are the standard of the art models. And yeah, so we chose that, and then we began by implementing this backbone, and on which we're going to build up. So yeah, we implemented this backbone in milestone one as well as the training loop, and we got our initial results. And from there, we faced the issue of class imbalance, which we decided to tackle in milestone two using data augmentation, as we basically had nearly three times as many pneumonia cases as the normal cases. So we had to oversample the normal case using a specific weighting ratio. So we did that using a weighted loss function, which we use basically a weighted cross entropy loss, and we calculated the class weights in an inversely proportional way to their frequency, and the final weights that we got were 1.94 for normal cases and 0.67 for pneumonia to oversample the normal cases, basically. Uh, Additionally, after that, we made changes to the architecture itself of the model by basically having customizable CBAM ratios per block instead of a fixed ratio in the traditional model. And also, we developed a certain variant of the model called DenseNet with extra conv end, which basically adds a sequence of convolutional layers, basically increasing the number of convolutional layers in our original model that we developed. And this allows basically to act as a better feature extractor for the later layers in the model. Uh, Other than that, we also implemented progressive freezing strategy, where basically freeze the for the first six epochs, we freeze the DenseNet backbone, like specific layers in it. And this allows basically new attention and convolutional layers to stabilize, and then we unfreeze the whole network for fine tuning. We kept doing this, and we also optimized the hyperparameters through trial and error. And we used the Atom optimizer with reduced learning rate and weight decay, and all of the parameters and values are in our poster and website.
So now we're moving on to our results. So for milestone one, we can see we achieved an accuracy of 81%, which is still higher than the doctor's accuracy of 70 to 80. However, we had a really poor recall for the normal class. But since this is a medical case, actually overdiagnosing pneumonia isn't that huge of a problem. However, we tried to fix the model to not just remember the pneumonia class, but to also really learn how to identify pneumonia in patients. So in milestone two, we tried modifying our model in four different ways. So for starters, we added four convolutional layers, which alongside our last model, which increased our accuracy from 81 to 87, which is a huge jump. When we try to increase the convolutional layers to six, our accuracy dipped, which is not really good. Also, we tried training the model with a fully connected layer without adding any convolutional layers, which achieved an accuracy of almost 90%, which is really great. You can see also in all of these cases, our recall problem has decreased significantly from our last milestone. Moving next for our last model, we changed the CBAM ratio. This resulted in getting an accuracy of almost 91. We didn't add any more layers. We didn't add a fully connected layer, just a modification in the hyperparameters, which is actually our highest achieving model. Now moving on to our milestone three, or the final milestone, we retrained the best model again. We retrained it by adding five extra layers. We trained it by adding a different loss function and a different optimizer, using focal loss, since we're using images, and using Adam W as well for our loss function. Here we can see the implementation attached in the slide, which achieved practically the same accuracy. It didn't really matter that much. Yeah, and that's it. Here we can see each team member's contribution, and that's it. Thank you so much.
I'm going to show you the demo for our project. Um, so now I'm currently loading the model. Here you can see I'm creating a model, the architecture to load the model into. Also here we have our state, the path to our model to load it. And then we're gonna use our GPU. Here we can see our model's architecture. Now we need to load the loaders. We're gonna use the test data set, and we're gonna load the images and labels to know the predictions and what our model predicted. Okay. Now we are gonna set our model to our evaluate mode. We're gonna get our probabilities and confidence for each one. Um, Here we can see our predictions. So we can see we're fairly confident when we are predicting correctly, like here 92, 82, 87, 88, 79. So we're fairly confident. However, when we get a wrong prediction, we're not confident at all. So that means our model is not just hallucinating as much. It's fairly confident in the pneumonia class, especially more than a normal class, since our dataset was kind of skewed. And here we can see the written format without the images. And that's it. Yeah.